Welcome to our first weekly live stream for college algebra. In today's live stream, we're going to focus on solving equations and inequalities with an emphasis on absolute value, polynomial, and rational. So we'll look at a couple examples. If you guys are watching the live stream and are logged in, if you can just type me a message in the chat field with your name, that way I know who's checking in. Also, any feedback that you guys have for this live stream is appreciated. This is our first run, and we want to make sure that we can improve it from week to week. So I need your feedback to do that. So we're looking at first an absolute value equation, the absolute value of x over 3 plus 2/5 equals 2. The emphasis on the definition of absolute value is going to be really crucial to understanding how we set up these equations and inequalities. Absolute value is referring to the distance something is from 0. So this statement that we have here, the absolute value of x over 3 plus 2/5 equals 5, tells me that this thing inside the parentheses is exactly 5 units from 0. Since the direction doesn't matter, that means I can be 5 units to the right or 5 units to the left. So I could be positive 5 or negative 5, which sets up my two equations. So I'm going to do that over here. So we have x over 3 plus 2/5 equals positive 5. That's going to be 5 units to the right. Or x over 3 plus 2/5 equals negative 5, and that would be your 5 units to the left. We solve both of these equations independently to yield two solutions. So I like this example because it's going to help us review some of those techniques for solving a linear equation, especially with fractions. So what we're going to do is try to clear all of our fractions by using the LCD. The LCD of this equation is 15, so I'm going to multiply both sides of my equation by 15. Oh, I'm sorry, that's a 2, not a 5. Sorry, guys. This should be 2 and negative 2. I don't know where I got the 5 from. Doesn't change the LCD. We can move ahead. That's fine. In this step that I just wrote, guys, notice I took the time to write out the distribution of the LCD. The nice thing about that is that then I can simplify each term individually without having to combine lots of steps at one time. When we start combining too many steps, that's when we typically start making careless mistakes. So in the first term, 15 divided by 3 is 5. 15 divided by 5 is 3. That should have been the 2 also. And when I simplify across, I get 5x plus 10 equals 30. No. What is wrong with me? Oh my gosh. Sorry, guys. I made a few mistakes here. This is a 3. You are probably all thinking, maybe this isn't what we want to participate in. And this is going to be 6. And I think we've fixed all the corrections, although nobody's yelling at me in the chat, so maybe we're good now. Sorry about that, guys. Again, I'm human, so I'm going to make mistakes too. Just make sure that you're always checking your work and making corrections as you go. If you don't bother to look back at your work in the middle of a problem, then you end up risking having to redo everything. Notice in this one, I was able to just go and make a couple of changes. It didn't require me erasing all of my work. But that's because I was looking at it as I moved ahead. So we're here. We've got 5x plus 6 equals 30. Subtract 6 from both sides. 5x equals 24. And I know we're on the right track now. Divide both sides by 5. One solution is going to be 24 over 5. Now leave this as an improper fraction. Do not convert to a mixed number, please. Over here in the second equation, we're going to do the same thing. We're going to multiply by the LCD of 15. And just like before, I'm going to show the distribution of that LCD so that I've got a factor of that LCD in every term that I can simplify with. Now I can simplify. 15 over 3 is 5. 15 over 5 is 3. And then we don't have any canceling out on the last term. We have 5x plus 6 equals negative 30. Subtract 6 from both sides. 5x equals negative 36. Divide both sides by 5. X equals negative 36 over 5. So we ended up with two solutions for this equation. Next, let's look at some absolute value inequalities. Absolute value of 1 minus 4x minus 7 is less than negative 2. We always want to start by isolating the absolute value. Whether it's an inequality or an equation, you want to isolate the absolute value first. So we're going to do that by adding 7 to both sides. So we have the absolute value of 1 minus 4x is less than 5. So now we want to talk more about the definition of absolute value. We're talking about a distance. What this statement says is that the distance of that thing inside the parentheses is fewer than 5 units from 0. So what are we referring to? If I set up a number line, here's 0. We've got positive 5 and negative 5 marked. Every value between negative 5 and 5 has a distance that is fewer than 5 units from 0. Look at some samples. 1 is fewer than 5 units from 0. Negative 4 is fewer than 5 units from 0. So this entire shaded region represents what could be inside the absolute value bar. It represents the 1 minus 4x. What this illustrates is that 1 minus 4x is between 5 and negative 5. And that's how we can use this idea of what absolute value represents to set up our inequality that we can solve. From here, we're going to subtract 1 from all sides. Negative 5 minus 1 is negative 6 is less than negative 4x is less than positive 4. Divide everything by negative 4. I'm going to give myself that visual cue, that asterisk, just to remind myself when I divide by a negative or multiply by a negative number, I need to flip the inequality symbol. So I'm going to go ahead and flip that first, and then I'll fill in the different pieces. Negative 6 divided by negative 4 is going to simplify to positive 3 over 2. X and 4 divided by negative 4 is negative 1. This we can flip around so that it's easier to read. Negative 1 is less than x is less than 3 over 2. The reason we like to flip that around, we think about reading from left to right, and numbers are increasing from left to right. The way we have it written originally, we're actually starting with a higher number and going to a lower number, so it's less intuitive. Now, if you need to, we can set up a number line to sketch the interval. The interval is from negative 1 to 3 over 2, not including either of our endpoints, and we can take our interval from that negative 1 to positive 3 over 2. Fix that. Three minus the absolute value of x plus 1 is less than 1/2. Same thing here. We want to isolate the absolute value first. Hey, Anna, I see you. Thanks for coming. We're going to subtract 3 from both sides. When we do that, we have negative absolute value of x plus 1 is less than 1/2 minus 3 is going to be negative 5 over 2. I'm pretty sure. Yeah. You guys can use your calculator to evaluate that, or use your margin to set up the subtraction. Now we've got to get rid of that negative. So I can either multiply or divide by a negative number. It doesn't matter. I'm going to multiply by negative 1. But again, when we multiply by that negative 1, we still have to flip the inequality symbol. So now this is going to become a greater than. We've got the absolute value of x plus 1 is greater than positive 5 over 2. So again, what does absolute value mean? Absolute value is talking about a distance from 0. So now this thing in the absolute value is more than 5 over 2 units from 0. So if we set up a number line, here's 0, here's positive 5 over 2, and here's negative 5 over 2. Where on this number line do we have values that are more than 5 over 2 units away from 0? Well, that's going to be everything to the right of positive 5 over 2 and everything to the left of negative 5 over 2. These shaded regions represent what x plus 1 could be. Now we set up our two inequalities. X plus 1 is less than negative 5 over 2, or x plus 1 is greater than positive 5 over 2. And we solve this, these two separately. We're going to come back to the emphasis on the word or when we go to write our intervals. Subtract 1 from both sides. We have x is less than negative 7 over 2. Or x is greater than positive 3 over 2. If we look at this on a number line, here's negative 7 over 2, here's positive 3 over 2. This first inequality is talking about values to the left of negative 7 over 2, not including it. And then the second inequality is values to the right of positive 3 over 2, again, not including it. So we see a similar shading as we did in our first graph to set up our new inequalities. Now to write our answer in interval notation, starting with the first interval, goes from negative infinity to negative 7 over 2. And our second interval begins at 3 over 2 and goes all the way to infinity. And because they're separate and we're talking about one or the other, we'll use the union symbol. X cubed minus 4x squared is greater than 0. So now we're shifting gears. We're no longer looking at absolute value. We're going to start looking at polynomial and then eventually rational inequalities. For our polynomial inequalities, we saw these in our first lecture video. We want to make sure that we set it to 0 first, which if we look at this example, if we can get it back up. This one's already set to 0. So our next step is to try to find the zeros. The easiest way to do that is to factor. So if I look at this and I try to factor this, I see I've got a GCF of x squared. And when I factor that out, I'm left with x minus 4. And this is still greater than 0. Once it's factored, we can find our zeros by setting each of our individual factors to 0. So our zeros are going to be at the value 0 and at 4. X squared equals 0 when x equals 0. This x squared is the one that people oftentimes forget, so be really careful with it. Set each factor equal to 0 if you're not certain with taking the shortcut. So now we want to set up our sign chart. We're going to mark our zeros, and we're going to test one value in each of those intervals. So we're going to test x equals negative 1, x equals positive 1, and x equals 5. These three values I chose for x are just, my choice. The only restriction is that the first one has to be less than 0. The second one has to be between 0 and 4. So we could have chosen 2 or 3 or any decimal between them, but that seems more difficult than necessary. And then any value greater than 4. So I'm going to take negative 1 and I'm going to plug it into my factored version to find the sign. Since all we're looking for is the sign, we don't really need to worry about the magnitude. If I plug in negative 1 to x squared, it's going to be positive. Negative 1 minus 4 is negative. So I'm multiplying a positive number times a negative number. That's going to be negative. When I plug in x equals 1, 1 squared is positive. 1 minus 4 is negative. The product of a positive and a negative is negative. Now, one thing I want to point out, this x squared, is it ever going to be negative? Well, if I take a positive number and I plug it in, a positive number squared is positive. But even when I plug in a negative number, it's going to end up being positive when I square it. So this first factor is always going to be positive. I don't even need to worry about it. 5 minus 4 is positive. The product of two positive numbers is positive. Since we are looking for where this polynomial is greater than 0, we're looking for the sections that yielded a positive value, which is from 4 to infinity. We're not including 4 because 4 is actually where the polynomial equals 0. So our final answer in interval notation is going to be 4 to positive infinity. Now we've had lots of practice with polynomial inequalities, so we're going to shift gears now and look at the rational inequalities, which we haven't seen unless you've watched some videos on my math labs or looked at some examples on my math labs. Now we set them up very similar to a polynomial inequality. There's just one extra step that we're going to take in this. So thinking back to the steps that we used to solve a polynomial inequality, the first thing we did was set it to 0. That's done for us. Then we wanted to find the zeros of the polynomial. We're going to do that here as well. The zeros, which are your x-intercepts, are actually where your numerator equals 0. So we can see that the zeros are going to be positive 1 and negative 1. What we're also going to find is we're going to find the restrictions as well. Now, if you recall, when you first learned about rational expressions and equations, perhaps in intermediate algebra or in another algebra course that you've taken, dealing with rational functions, we can't have 0 in the denominator. So we restrict the domain, saying x cannot equal such values that make the denominator equal to 0. Those values we call our restrictions. So in this particular problem, our restriction is going to be at 0. So the restrictions, again, come from the denominator, and those are going to be the values that would make your denominator equal to 0. We go on to our sign chart, and with our sign chart, we're going to put our zeros just like we did for a polynomial inequality, but we're also going to list our restriction. So we've got -1, 0, and +1. And I'm going to put a little asterisk next to the 0 just as a reminder that that's a restricted value. So when we go to write our final answer, if perhaps we might think we should include it, we can't since it's not in the domain of that expression. Okay, same thing. We're going to test a value in each interval. So let's try -2, -1/2, +1/2, and +2. We can use the factored version as well, and we're going to do the same thing where we just are finding the signs of our factors because that will be enough information to determine the sign of the polynomial. When we plug in x equals -2, -2 minus 1 is negative, -2 plus 1 is negative, and then -2 is negative. We've got 3 negatives here. If I multiply the 2 in the numerator, that gives me a positive value, but then I'm dividing by a negative, so it's still going to be negative. Kind of a shortcut rule for this, determining the sign. Whether you're multiplying or dividing, the rules are going to be the same. If you have an even number of negative signs, the value is going to be positive. If you have an odd number of negatives, it will stay negative. Okay? -1/2. -1/2 minus 1 is negative. -1/2 plus 1 is positive. And -1/2 is negative. So here we see that we've got an even number of negatives. So the sign is going to be positive. When we plug in +1/2, 1/2 minus 1 is negative. 1/2 plus 1 is positive, and 1/2 itself is positive. So in this one, we have an odd number of negatives. The sign is going to be negative. And just to justify this one more time, if we think about the numerator, we're multiplying a negative times a positive. A negative times a positive is negative. And then we're dividing that by a positive number. Negative divided by a positive is negative. So we can see that the rules for the even or odd number of negatives, it doesn't matter if it's just straight multiplication or if it's multiplication in addition to division. X equals 2. 2 minus 1 is positive. 2 plus 1 is positive, and 2 itself is positive. We have all positives, which will yield a positive value. Now, looking at the problem, we want to know where it is less than or equal to 0. So we're looking for the negatives. Let me use a different color real fast. So we're looking at this section and this section. And the question now is, which of these endpoints do I include? Do we include -1? The answer is yes, because -1 is actually a 0 of the polynomial. I want to know where the rational expression. I want to know where the rational expression is less than or equal to 0, so we include that value of -1. What about 0? We are not going to include 0 because 0 is a restriction. It's not even in the domain of the expression. Okay, that little asterisk is going to help us remember that. And then the 1, since that is a 0, we will include it. And to finalize our answer in interval notation, ooh, I just lost a feed over here, guys, if you can fix that. Doesn't really matter. Sorry, guys, technical issue. Back to the problem. If we're writing this in interval notation, our first interval is from -infinity to -1, union 0 to +1. Okay, so looking back at our work, I just want to highlight the differences between solving the rational inequality as to the polynomial inequality. And the only real difference is that now we're also looking at the restrictions, so where the denominator equals 0. And that's going to be an extra separation on my sign chart. So I've got, I think, one more example for us before we finish up. Another inequality, a rational inequality, x plus 4 over x minus 2 is less than or equal to 1. Think back to those steps for solving a polynomial. The first thing we want to do is set it to 0. So we need to do that in this problem. So we need to subtract 1 from both sides, which looks a little funny. So we've got x plus 4 over x minus 2 minus 1 is less than or equal to 0. Now, in that previous example, we talked about finding the zeros of the numerator and the zeros of the denominator, but we only had one fraction. Here we've got a fraction and a constant. We need to combine those and write them as one fraction, and we use a common denominator to do that. For this, the common denominator is going to be x minus 2. So we're going to multiply that -1 by x minus 2 over x minus 2. I'm going to come over here so I have a little bit more space. We have x plus 4 over x minus 2 minus x minus 2 over x minus 2 is less than or equal to 0. And now that both of those terms have the same denominator, we can combine them as one fraction. Be careful with this minus sign, though. I'm subtracting the entire second numerator, so we're going to need to use parentheses. X plus 4 minus x minus 2 all over x minus 2 is less than or equal to 0. Distribute the minus sign. X plus 4 minus x plus 2 over x minus 2 is less than or equal to 0. Combine like terms. In the numerator, the x's are going to cancel out. We have 6 over x minus 2 less than or equal to 0. And now we have an expression that looks like that's just one rational expression. In the last problem, we tried to find the zeros, which were in the numerator, and the restrictions, which came from the denominator. The zeros, which would come from the numerator, well, my numerator is 6. Is 6 ever going to equal 0? No, so there are no zeros. My restrictions, which would come from the denominator, is going to be +2. So when I set up my sign chart, I'm only going to have one value, and it's going to be a restriction. Since it's a restriction, I'm going to mark it with that asterisk just to indicate when I go to write my final answer that I would never include that value in any interval. So testing a value in each interval, we're going to test x equals 0 and x equals 3. And we're using, again, that final version of the inequality, the 6 over x minus 2. The numerator is always going to be positive because 6 is positive. And then 0 minus 2 is negative. Positive divided by a negative number is negative. When we plug in x equals 3, the numerator is still positive, and 3 minus 2 is also positive. So the quotient will be positive. We're looking for where the inequality is, where the rational expression is less than or equal to 0. So that's our negative section. Are we going to include the value of 2? Because it does say equal to. The answer is no, because 2 is a restriction. It can't be included in any interval. So our final answer, negative infinity to positive 2. Okay, that wraps up our review on absolute value equations and inequalities, polynomial and rational inequalities. Hopefully you guys find that the rational inequalities are very similar to the polynomial inequalities. You just have that one extra value you need to find, or set of values, which would make the denominator equal to 0. I want to remind you guys that we will be hosting these live stream sessions every Wednesday at this time at 3:45. And if you guys have a Google or a YouTube account, you can log in and you can ask me questions throughout the stream, which is really what we're here for. We're here to help you guys. If you're able to get these examples done ahead of time, then you have some prior knowledge as to what you were confused on, and you can ask me those questions and I can address them live. So we appreciate you guys participating, and we hope to see you next week. Have a good day.